All right, here is so I finished this quantum physics. We talked about this, I think, on the last podcast about quantum physics. So I finally finished Michio Kaku's book, Quantum Supremacy, and it was about quantum computers. Do you know what a this is so dumb. I love how they make it sound so like intense, and then you find out what it is, you're like, actually really simple. Do you know what a quantum computer is? Boiled down, basically what it is.
I think I saw your post on it. It's just
Oh, okay.
quick. It's just faster computer or whatever. Like the
It's just a goddamn powerful computer, bro.
yeah yeah.
I was like, okay. Like, but if they make them smaller, they can add more chips and
Mm-hmm.
more processors. So like right now, let's say you have the the chip the size of like, I don't know, my thumb, right? But if you can shrink that down to like a quantum level, like an even like you can fit one thing I've been hearing is like you can store data on a DNA strand
Right.
now.
Okay. Oh,
So it's like they're trying to go as small as possible because then you can compact
information.
data,
Yeah.
right? And some people believe that like that's what our DNA strand holds, like data.
Mm-hmm.
You know, 'cause people have said like in spiritual texts, like the answers of the universe are hidden within you. So it's like maybe if we can create like a computer that can read it. And the reason why you need so if you listen to people who are building these quantum computers, it it needs like a very stable environment and a very cold environment.
Mm-hmm.
Makes sense
Yeah.
though,
Yeah.
because what about if you're running something just like my computer right now? It's hot outside. The fan has to work like 3 times as hard to not make it explode,
Yeah.
right? So like if you're using something with a lot of energy, you need a really cold space,
Yeah.
you know. And then the
Mm-hmm.
reason why they need it to be as stable as possible is because you're dealing with chips on such a tiny level. If you nudge it just a bit, you're going to mess up the circuit.
Mm-hmm.
So it makes sense. We're just building things at a smaller level. And then the smaller you go, the more processors, the more speed, all that, et cetera, right? Because if you look at the size of the M1 chip now, it's identical to like the size of another chip. But the reason why it's so fast is because they were able to like fit more
Fit
in a
more.
tiny space.
Yeah.
Fit. Okay. Um, that wasn't the revolutionary part about this book.
Mm-hmm.
The revolutionary part of this book was finding out what quantum physics is. Because that's what, and so what they're saying is if they can build a small enough computer, they could probably tap into these quantum properties.
Mm-hmm.
Okay. And I'm like, now we're getting crazy, everyone. So I'm going to read you the four. Did you see this yet or no? Like, did you see my post about the quantum
You're
physics properties?
no. I didn't see that one.
Okay. So, so it's only four things
Okay.
that they found for quantum physics. So first one's superposition. So we know that through Schrodinger's cat. Basically, I'm just going to read it directly. That's why I needed my phone, but Tara wanted to use it, so we're using screenshots.
Mm-hmm.
Superposition. Before you observe an object, it exists in many possible states. So an electron can be in two places at the same time. This vastly increases the power of a computer since you have more states to calculate with.
Mm-hmm.
That's what they're trying to do, right? So if they can get small enough, you can get like multiple states for the computer. So again, this goes back to free will. It's like if the atom is like in multiple states, which is the true state? Like, choice then. 'Cause
Sure.
like, which one are you going to go with? Okay. There's only four. Next one, entanglement. When two particles are coherent and you separate them, they can still influence each other. This interaction takes place instantaneously. This allows atoms to communicate with each other even when separated. This means that computer power grows exponentially as more and more qubits are added that can interact with each other far faster than ordinary computers. So the smaller you go, like these atoms, even if they're like separate, if you move one, the other one moves too.
Mm-hmm. Okay.
Right. Okay. So first, multiple different options. The second, they're entangled. So as you move one, the other one moves too. Okay. Sum over paths. This one's a little tough for me. When a particle moves between 2 points, it sums over all possible paths connecting these 2 points. The most likely path is the classical non-quantum path. but all these other paths also contribute to the final quantum path of the particle. This means that even paths which are extremely unlikely may become real. Perhaps the paths are perhaps the paths of molecules that create life become real because of this effect making life possible. So basically, and this is what my question was with quantum. If determinism's not real, how can probability mathematics work?
Mm-hmm.
You know, like
Yeah,
if I
yeah,
make a calculation should work, that's why they're calculations, right? So what it's saying is that if I want to shoot the ball from here to here, it will most likely follow the non-quantum path, meaning that our calculation on a non-quantum level will be accurate. The ball will move to where we want it to move. However, all of the possible states are happening simultaneously, but they show up where we want them to go.
Mm-hmm.
Doesn't mean that those aren't real. It just means that traditionally, like on a non-quantum level, it will follow the path. But it could technically go off path, but it's highly unlikely.
Mm-hmm.
Again, that's why science works. It's like, because I was like, if quantum's real, how can we do mathematics?
Yeah.
How can we like physics, basic physics, trajectory, you know? But it's saying that, you know, all of the possibilities are there. What we're seeing is just the non-quantum version of it. Technically determinism. Okay, last one. Tunneling. This is the craziest one. When faced with a large energy barrier, normally a particle fails to penetrate it. So what it's saying is, you know, when we touch each other, we're not actually touching. Our atoms are not touching. There's like a force field.
Yeah.
We know this, right? Basic science. That's why we don't phase through each other.
Yeah.
Right? So we're never actually touching each other. We're just literally hitting a barrier. Okay. So it's saying with the barriers. But in quantum mechanics, there is a small but finite probability that you can tunnel or penetrate through the barrier. This might be why the complex chemical reactions of life can proceed at room temperature even without vast amounts of energy. Okay. So that's why they're trying to build this really, really tiny computer, because they can get into these 4 states. Okay. Sounds nuts. One more thing to read to you. For example, if we hypothetically live in a quantum world, it means that everything we know about common sense is wrong. For example, so if quantum physics is real, if we live in quantum physics reality, then common sense is incorrect. And here are the examples of common sense. We can be in 2 places at the same time. We can disappear and reappear somewhere else. We can walk through walls and penetrate barriers effortlessly, which is called tunneling. People who have died in our universe might be alive in another. When we walk across the room, we actually simultaneously take all the infinite possible paths across the room, no matter how bizarre. What the hell are we talking about now?
We're talking about
I don't
the
even know
show
if I
Dark
believe in
Matter.
quantum. Oh, really?
Yeah.
Oh, that's all in there?
Yeah, that's what's happening to the guy, because he's different. Not different universes, different
Is he
multiverses.
phasing too?
He's the box is what makes them go through to the next or another world.